In this video, we're going to learn about periodic trends, effective nuclear charge, atomic radius, and ionization energy. We'll have a second video on the other periodic trends, electron affinity, electronegativity, metallic and nonmetallic character, and reactivity. So it may seem like there's a lot here, but actually all the periodic trends can be explained through Coulombs Law. And Coulombs Law is just the law that explains the attraction of a positively charged particle and a negatively charged particle. So if we have, say, in the atom, a nucleus that's positive and an electron that's negative, there will be some force attracting them, and that is proportional to the magnitude of the charge of the nucleus times the charge of the electron, which always is -1, divided by the distance separating them squared. So the more charge there is in the nucleus, the more strongly attracted the electron will be to the nucleus. However, the further apart those two are, the lesser the attraction between them. I think the magnitude of charge relationship is fairly intuitive. More charge, more attraction. With distance, I want you to think of magnets. Magnetism and electricity are not quite the same, but they're very similar in terms of the forces involved. So if we have two magnets that are close together, they'll really feel each other, but as we separate them, they won't feel each other nearly as much. So as R increases, you get lesser attraction between them. So with Coulombs law, we can use that to explain the attraction of the nucleus for the electron in hydrogen and the helium ion, He positive. In this case, the electron is in the same shell for both, but the helium ion has a more positive nucleus, so there will be a stronger attraction between the nucleus and the electron in helium positive than in hydrogen. So that's manageable, but when we get to more charged particles than 2, it really complicates things. So let's consider not the helium ion, let's just say the helium atom, where we have a +2 nucleus and 2 electrons to even out the charge. This is still a very simple, small atom, but you can see that this is much more complicated because you've got attraction of the nucleus to one electron. You've also got attraction of that nucleus to the other electron. Meanwhile, the electrons are repelling one another. And so there's just a lot more going on, especially given the fact that this is a dynamic system. The electrons are moving around continually, and that changes the attraction of the electron for the nucleus and the repulsive effects between the electrons as everything that is moving continually. So what we have is something called effective nuclear charge, which is used to make this a little bit more manageable, to understand the attraction of an electron of interest, which with periodic trends, we're only ever talking about the valence electrons, the outermost. So we've got the outermost electron and we've got the nucleus. They'll be attracted to each other according to Coulombs law, except, well, there will be core electrons in between the electron that we're considering and the nucleus. And those core electrons will be shielding the valence electron from the nucleus. They'll be lessening the attraction of the nucleus to the outermost electron just by getting in the way. So if we look at this chart here, what we find is that as we go across a period, the effective nuclear charge increases. So lithium, beryllium, boron, all the way to neon, they're in the second period, and there's a very consistent linear increase in effective nuclear charge as we go across the second period. Same with the third period. So what we find is that as we go further to the right, we're going to have higher effective nuclear charge. Also, what we can find, lithium and sodium are in the same group, so we can make a comparison as we're going down the periodic table. what we'd find is that potassium and cesium, forgot rubidium, cesium, francium, they'll be higher still. So what we find is that the effective nuclear charge increases also as you go down a group. So how does effective nuclear charge and how does Coulombs law affect atomic radius? First, we need to define atomic radius. If we look at an atom as a sphere will have a radius. Atomic radius is just the radius of the atom. Let's look at this periodic table where we have the atomic radii shown. So what we find is that the smallest atomic radius is that of helium, 31 picometers, and the greatest is cesium, 298. That is an enormous difference. But you can tell as we go to the right, we get a decrease in atomic radius, regardless of whatever period we're going across, whether it's period 1, period 2, or any other period. The further right we go, the smaller, and the further up we go, the smaller. So the largest atomic radii will be on the left and down. And let's explain why, using Coulombs law. So what we can say is that as we are going as we're going down a group, there will be less attraction between the nucleus and the outermost electrons because the outermost electrons are in a higher energy level. If I've got an electron in sodium in that third shell, even though there are more protons in sodium than in, say, lithium or hydrogen, because there's so much shielding of the core electrons, and because the valence electron is so far away in the third shell, we can say that the attraction between this outermost electron in sodium and the nucleus is less than the attraction between the electron in hydrogen and its nucleus. So number of shells correlates with the size of radius. The greater the number of shells, the greater the radius. Now let's consider going across a period. What we can see here is that as we go right across a period, we find that the atom decreases in size. How can we explain it? Well, we know that lithium has 3 protons and that beryllium has 4, and neon has 10 protons. So as we go across the period, we find that we increase the nuclear charge, meaning that Coulombic attraction is going to rise. And really importantly, we're adding electrons to the same shell. We're just adding an electron to the second shell, another electron to the second shell, right? As we go across, there is no extra shell. That only happens when we go down a group. And critically, the amount of shielding is not going to increase particularly much because notice the core electrons in lithium, 2, are the same as the number of core electrons in neon, still 2. So we're increasing the number of protons and we're keeping the shielding more or less the same because of the fact that there are only 2 electrons in all of these elements in the first shell. Next, let's consider ionization energy, which is something that we have studied in the Bohr model, the amount of energy required to remove the highest energy electron from an atom. If we're talking about hydrogen, it will take a certain amount of energy to bring that electron not from the first to the second shell, but from the first to the infinity shell, which is the ionized state. But if we were talking about any atom, there would be an ionization energy, just that's the energy required to raise whatever the highest energy electron is. In the case of sodium, it has a 3s electron as its outermost electron. So what is the energy required to take that 3s electron and raise it to the state that it no longer is associated with the nucleus, that it's no longer attracted to the nucleus, it's so far away. So ionization energy, if we look at this chart, we'll find the highest is at helium and the lowest is actually cesium, not francium, which is a bit surprising. So So in general, though, we can see that as we're further to the right and we're further up on the periodic table, we have higher ionization energy. Notice it's pretty blue over here to the right and up, and less so bottom and left. So how can we explain this? Let's consider a trend within group 1 as we go down the group. We have one proton that hydrogen has and one electron in the outermost shell, which is the only shell. There's quite a bit of Coulombic attraction between them, and so it's a bit hard to take that electron and fully remove it from the attractive pull of the nucleus. In the case of lithium, we have more protons. However, we have some core electrons that are shielding, and that outermost electron is much further away from the nucleus than in the case of hydrogen. So what we find is that as there are more shells, that electron in a higher energy level is easier to remove. Now, in the case of going across a period, we're not taking electrons and adding them to higher energy levels. Across a period, we know lithium has electrons in the second shell, and that's the highest energy electron will be in the second shell. Neon still, its highest energy electron will be in the second shell. And that actually can be used to explain the trend as we go to the right, we have higher ionization energy. Because as we go to the right, we're adding protons to the nucleus, we're increasing the effective nuclear charge, and we know that the attraction of the nucleus for the outermost electrons is increasing because the atomic radius is getting smaller. As we add protons, the valence electrons are getting closer and closer and closer to the nucleus because they're being pulled in more. And similarly to that contraction, well, we're making it harder to rip off the outermost electron, which is why we see this trend, more ionization energy as we go across the period. That's as far as we're going to go in this video. The second video will have more on the periodic trends, starting with electron affinity. Hope you've enjoyed. Feel free to give any feedback or ask any questions in the comments. Thank you.